Good day, everyone. So, in today's lesson, we'll be looking at the topic waves. And at the end of the lesson, we'll be able to define what a wave is, the type of wave we have, and the characteristics of wave, as well as the terms that are used in wave. And lastly, the calculation involved in the introductive part of wave. All right, so what then is a wave? A wave, as you could see an example in this diagram, is a disturbance that propagates through a medium. You can see this ocean. Ordinarily, this ocean will have remained calm if there was no wave. Okay, but you could see the wave moving to and fro. So it's a disturbance. This disturbance makes this ocean to be moving to and fro, up and down. So a wave is a disturbance that propagates through a medium. In this case, the medium is the ocean, transporting energy from one location to another. You see now? So, number one is known as a disturbance, and then two, it now transports energy in that medium from one location to the other. This medium can be solid or liquid in the case of the diagram we have here, an ocean. But sometimes it can be solid, it can be liquid, it can even be gas. So the medium through which wave travels can be either of this state of matter, solid, liquid, or gas. However, the type of wave that require material medium to travel is called mechanical wave. There are some waves that do not really require material medium before they can transport energy. Okay, such type of wave we do not call them mechanical wave. They are known as electromagnetic wave. So the one that require material mediums are called the mechanical wave. The one that do not require material medium to transport the energy are known as the electromagnetic wave. All right. So then we now say that we also have types of mechanical wave. We have just said that wave can be categorized into two based on whether they require material medium or not. Now, if they require material medium, we call them mechanical wave. If they do not require medium, okay, to travel, then we call them electromagnetic wave. But then for those that require material medium, which are called mechanical wave, they are also divided into two types, and they are longitudinal waves and the transverse wave. The longitudinal wave under mechanical wave are a type of wave which the particle of the medium vibrate parallel to the direction of propagation. Okay, so in this type of mechanical wave, the particle of that medium always vibrate in parallel or the same direction with the direction of the propagation. All right, and a good example is the sound wave. As you could hear me now, you can hear the sound of my voice because sound is an example of longitudinal wave. In this case, what do I mean now? As I am making sound, the sound is going through a medium called air. So the air particle begin to vibrate in parallel to the sound I'm making. So that is how we refer to it as longitudinal wave. Okay. Now, the other type of wave that do not, which particle of medium do not move in parallel, but rather move in angle 90 to the direction of wave is called the transverse wave. So in transverse wave, the particles of the medium vibrate in perpendicular direction to the direction of the propagation of wave. And a good example of this kind of wave is called the water wave. Just like the one we saw in our previous slide, the ocean wave is an example of water wave. Okay, so another example is the wave that we have in a rope. You know, when you vibrate a rope, a string, the vibration of the particles of that string is usually at 90 degrees or perpendicular to the direction of wave. So basically, we say that mechanical wave are two types: the longitudinal wave and the transverse wave. So now, how do we produce wave? How do we produce mechanical wave actually? Now, mechanical wave, we could say that waves that require material medium, and this medium can be solid, liquid, or gas. Now, in solid, if you want to produce mechanical wave in solid, just vibrate that solid uh, material. Just vibrate it. For example, now if your phone is ringing, there's a device called vibrator, and that vibrator is vibrating, is generating a wave. Okay, so whenever there is a vibration of solid object, wave is being vibrated. Another one is your jitter. When you vibrate your jitter string, it's generating what? A wave. Okay, then aside from vibrating the object, another way you can produce a mechanical wave is through collision. When you collide two objects together, okay, then they create what we call mechanical wave. If you get two solid objects and then you hit them together, they begin to vibrate. That vibration has generated mechanical wave. All right. Another way you can produce a mechanical wave is through pressure changes. Changes in pressure can also create mechanical wave when we increase the pressure or we decrease the pressure. For example, as I'm talking now, the sound wave I'm producing can either have high pressure or low pressure. When the pressure of my sound is high, that is when you can hear me loudly. It means that the pressure of the particle of vibration of air is high. Okay, but when the pressure is low, then you will only hear me, barely can you hear me. So the higher the pressure of the particles, the more you hear, because the material medium for sound wave is air. All right, so these are the three ways you can produce mechanical wave. Now, how do you now propagate mechanical wave? It's one thing to produce it, it's another thing to propagate it. Propagating means spreading it. Okay, there are two factors that affect the speed, the spreading. When the wave is moving, is spreading. Now, there are two major factors that affect that speed of a wave: the frequency of that wave and the wavelength of the wave. So by formula, you could see here that the speed of the wave, which is v, is equal to the product of the frequency of the wave and the wavelength. The f is the frequency, while the lambda, last symbol is called lambda, is called the wavelength. So the product of frequency and wavelength gives you the speed of the wave, and this is called the wave equation. All right, now we have talked about how you can generate mechanical wave. Okay, now there's what we call pulsating system. Okay, a pulsating system involves continuous oscillation of a source, generating waves that carry energy outward without transferring matter. Now, every wave has a source, and that source is what keeps the wave ongoing. So when that source is not taken away, then it creates what we call pulsating system. All right, and a good example of a pulsating system is a ripple tank. Okay, a ripple tank is just a shallow tank with a light source, as you can see here, with a light source and barrier. Okay, when you move the barrier up and down, it creates waves that propagate across the water surface. So this is a diagram of a ripple tank. You can see that there are waves in this water now because the tank contains water. Now the source of this wave, okay, is coming from a disturbance. Okay, the source. Now as that source of the wave keep producing a disturbance, keep beating that water, it keep generating all this wave we are seeing. Okay, so that process of beating the water continuously is called a pulsating system because it's a continuous oscillation of the source. All right, and when we say wave is a disturbance that will transfer energy. Any wave that is being propagated must also will transfer energy. Okay, so when wave is being propagated, energy is also propagated along with it. All right, so that's what we also call the waveform. A waveform is just a visual representation of how the amplitude of a wave changes over time or space. So you use a diagram to represent how a wave is being propagated, and that diagram is what we call the waveform. You see that this is a typical diagram to represent the propagation of a wave. So this point here is telling us the source of the wave, and then the wave begin to move. You see, it's moving like this. This movement is called sinusoidal kind of wave. Okay, so we use sinusoidal wave symbol to represent the graphical part of a wave. Okay, so when you want to represent a wave with a graph, you use what is sinusoidal graph. You see, we also have other types of graph. The square type, where you see square shape. We also have triangular type, but the one we use for waveform for our level is sine wave, sinusoidal graph. Okay, so that's what we use. Now let us say some things about this graph. Now this graph, of course, has the vertical axis. It also has horizontal axis. Now the vertical axis represents the amplitude. Okay, the amplitude is the maximum height that the wave attains before it comes down again. All right. So the vertical axis represents what? The amplitude axis. While the horizontal axis represents two things. It could represent the distance traveled by that wave. It could also represent the time it takes that wave to travel. So this horizontal axis represents either distance or time. All right. So the wave begins to travel like this. It goes attain maximum height, which is amplitude, and then come down again, and then attain minimum height again, which is the amplitude, and they keep going up, down, up, down. So this graph represents the propagation of wave, and we call this type of wave progressive wave. Now, when the wave begin to exhibit this sinusoidal wave, now this top here, this shape here, this curve here, we call it crest. While the down part, whenever it is at the down part, we call it trough. Now the distance between two consecutive crests, that is this crest and this crest, the distance between them is called wavelength. Also, distance between two consecutive trough is also what? Wavelength. All right. But when you say this crest and this crest now, let me butcher what I'm saying. Maybe you have a crest. Now look at this. This one crest here. This crest one. Let's call this crest one. This crest two, and this crest three. Now, distance between crest one and crest three is not wavelength because there is a crest in between them. But when you talk about wavelength is always distance between two consecutive crests. When I say consecutive, I mean next to each other. So the wavelength is always distance between two consecutive threads, because you could see it here, or two consecutive trough. So you call it what? Wavelength. All right. Now the amplitude, of course, is the maximum displacement attained by the wave. It moves from here and attain this height. Okay. So this maximum height is called amplitude before it now goes down and continue in motion. Okay, so these two major terms are important. Amplitude, maximum displacement attained by the wave, while wavelength is the what? Is the distance between two consecutive crests or two consecutive troughs. Crest is the maximum height attained, trough is the minimum, okay, the minimum height attained. Okay, so it's very important that we understand those terms as we continue. Now, we've talked about amplitude as one of the key waveform term. Amplitude, we say the maximum displacement that is being attained by the wave. We talk about wavelength, the distance between two consecutive crest or trough. Okay. Now, we also have what we call the frequency. Frequency is the complete oscillation per second. Okay. Okay. In other words, the number of oscillation or number of cycles attained in 1 second. Okay, so if you go back to the previous slide, This is circle. We are going to demonstrate this now. This is circle. Now from here, from this point like this up to this point, this half circle, this another half circle. So this is what? This is one circle. Now another circle goes from here, half and half. This is another circle. So these are two circles now I've done now. Now the number of circles you're able to cover in a second is what we refer to as frequency. So frequency is the number of circles covered in 1 second, or number of oscillation. Another one for circle is oscillation. Okay. Then we talk about crest. We have said the crest is the highest point above or the lowest point. We've talked about that. Then period. Period and frequency, they are what? Opposite. Why frequency is the number of circle or number of oscillation covered in 1 second. Period is the time taken to complete one circle on one oscillation. Then the last one is phase and phase shift. Phase actually is the position that the wave is at the particular point in time. Then phase shift is the distance between the previous position of the wave and the subsequent and the next position of the wave at a particular time. So phase is measured in degree, or phase shift in degree. Period is measured in seconds. Wavelength is measured in meters. Amplitude is measured in meters. Frequency is measured in hertz. Of course, crest and trough are just the maximum height or the minimum height. So they can also be measured in meters. Okay? Now, sound wave, we have said it earlier that they are example of mechanical wave under the example of longitudinal wave under mechanical wave, because they are particle of the medium particle vibration is always parallel to the direction of the wave. That's what sound wave is. Okay. Now the point where we have high pressure is called compression. The point where we have high pressure of the air, so that you can hear someone very well. Remember, we have said that sound wave require air as medium to be transported. Now that point where you have high pressure is called compression. Where the point where you have low pressure is called rarefaction. Low pressure of the air is called rarefactions. All right. On the other hand, light wave is an example of electromagnetic wave that do not require material medium. This is the only wave that can travel through vacuum. You see other wave, they can't travel through vacuum because vacuum is an empty space. Okay, and it is obtained by the combination of electric and magnetic component. So electromagnetic wave is formed by the combination of electric and magnetic component. That's why it is tagged, or it is named, electromagnetic wave. Okay, so let us look at one or two examples before we call it a day. Now look at this question here. It said, if the wavelength of a wave traveling with the velocity of 360 meters per second is 60 meters, the period of the wave is what? A, 6 seconds, B, 3.6 seconds, C, 0.17 seconds, D, 0.61 seconds, and E, 3 seconds. Okay, so in our usual form, let us write out the parameters. Again, if the wavelength of a wave is traveling with a velocity of 360 meters per second, so here we are given a velocity, and the velocity given is 3 meters per second. So 360 meters. This is the velocity given to us. So that's V. So our V is given here. V in the question is given to be 360 meters per second. Then what else again? We are given the wavelength. Remember, I said if the wavelength of a wave traveling with this velocity is 60, so our wavelength is lambda. So lambda is 60 meters. So we have to find the period. The symbol for period is capital T. How do we get the period? That's the question. Remember the wave equation, that speed is equal to frequency times wavelength. Okay. Now from here, we can now get our frequency. So our frequency from here will be V over lambda if you divide both sides by lambda. And our V is 360 over our lambda is 60, right? So 0 cancels 0. 6 here 1. 6 in 36 is 6. So that is 6s. But then we are not how to find frequency, we have to find period. Good. But the formula for period, capital T, is equal to 1 over frequency. So that is 1 over 6, right? So 1 over 6. And that will be giving us what? You can just say 1 over 6 second, because period is measured in second. Then in decimal, you can say 0 point, okay, 0.1. Then 6 in 10 is 1, remainder 4. Then 6 in 40, that's 6, 0.16 second by decimal form. Checking the option, we have 0. We have A to be 6 seconds, we have B to be 3.6 seconds. That is not 0.17. That will be the closest answer approximately. Then D is 0.61 second and A is 3 seconds. So if we go ahead to do up to the third decimal place, we will say that our answer will be what? 0.16. Let us confirm that. Again, or if you don't want to waste your time, you can get a calculator and do this. Now, is 6 in 1 is impossible, that is 0 point. So put your 0. 6 in 10 is 1, remainder 4. 6 in 40 is 6, remainder 4 again. In 40 is 6. So two decimal places will be 0.17 seconds. So the correct option here is 0.1, that is option C, right? Now, we also have another one. That's question 4. Let's create a space for our next question. Okay, our next question does not necessarily require us to do any much calculation. Let's quickly look at it together. Now, in this question, the question is saying that for the wave motion represented in the figure, the wavelength, for the wave motion represented in the figure, what will be the wavelength given by? The wavelength is given by, okay, that's the question. The wavelength is given by what? Okay, is it by P? Where is P? This is P from this point to this point. That is not our wavelength. Remember what our wavelength is. So it's not P. So is it Q? Q is not Q. Look at where Q is. Q between from here to here. That is not true. Is it R? Where is our R? Our R is here from here to here. That's not true. Is it X? Where's our S? This is our S from here to here. That's very true. We said wavelength is what? Distance between two consecutive crests. So S is the correct option. It cannot be T. Okay. Where's our T? T is from here to here. Okay. So the correct option is D. That's distance between two consecutive crests. All right. So we'll be drawing our curtain here today. I hope you have learned something on the concept and introduction to wave. Thank you for listening, and bye for now.